Good morning. As she said, my work is with Thiosemicarbazones, their ligands, and their copper complexes. So this just gives you a brief overview of what we'll be talking about today. Thiosemicarbazones are a class of ligands that have been shown to inhibit topoisomerase, which is one of the key components of breast cancer cells. These compounds also have a high affinity for metals, particularly metals that have a +2 charge. We've synthesized a new series of thiosemicarbazones, which are propionyl thiols, and the two main ones that I'll be talking about are propionyl thiazole, our ethyl compound, as well as our terbutyl compound, and their corresponding copper complexes. The general procedure that we do in order to form the ligand is actually a very standard in-house procedure for thiosemicarbazones. And in order to do this, we take a 1 molar ratio of propionyl thiazole with our thiosemicarbazones, and then we combine them together in a reaction mixture, usually using either ethanol or methanol. We add a bit of sulfuric acid and then leave it to stir overnight. These generally come out to be very, very pure, and so then we proceed on to our copper complexes. This is also a very standard procedure, and what we're doing here is that we take, again, a 1-to-1 molar ratio of our ligand that we form, as well as copper chloride. And now, because this is a tridentate ligand, it goes through a synthesis procedure where it exchanges the water and the chloride, and in order to get the form that you see here. The anion here with the hydrogen, and it is where you see this happen in this form right here. We proceed on then to test it within our NMR machines. And so we're testing, here we aren't able to test the copper due to the resonance, but we are able to test the ligands themselves. What we've seen with the ligands is that they generally come out in two forms, particularly with the ethyl. Now we're able to see this here with this hydrogenic proton as well as this, which corresponds up here. What we found though is that when you go through a purification process, we can eliminate this for the most part and get a very, very clear compound. And so that's how we know that what we have inside it is able to go on to the next step once we've gone through purification. Now, this here is representing the crystal structure for the propionyl thiazole terbutyl. This is the solution that we get, and it's this beautiful green color. And what actually happened here when we formed these is that one day I randomly decided to add twice as much methanol as I would typically add. And what we saw was just the solution and no product was formed, whereas typically we get a lot of very powder crystalline structures come out. We stuck it in the freezer over fall break, which was for about 5 days. And when we came back and pulled it out, we saw these very, very large crystals here in the bottom. We then sent this off to the University of Alabama, who came up with a crystal structure for us. What we found is that although copper typically likes to be in an octahedral shape, that because of the nature of our thiosemicarbazones, it actually forms a square planar structure. Down here's the ChemDraw structure that you can see, and it did confirm what we were expecting to find in our propionyl thiazole terbutyl copper complex. The most important part of this, of course, though, is going to be the application. And so the point is to target topoisomerase, and we believe the active site is right here in the middle between the different subunits. Now here is one of our assays, and here is a no topos. This is strictly DNA. This is what we're trying to get down to. We have a no drug column, which is where we've added the topoisomerase in. And when we use the ligands for both the ethyl and for the terbutyl, we find there really isn't much relaxation down to the supercoiled DNA at all. However, when we did a 50 micromolar concentration of the actual complex, we found that it worked extremely well. We had very little lag still left up here, and it was pretty much all condensed back down. But because that was so much, we weren't able to tell exactly where it was active at. So we moved on to doing a drug dose dependent concentration study. Here, once again, we have the no topo and the no drug, and then we proceeded on through 1 micromolar up to 10 micromolar concentrations. Now what we found is that with the ethyl, we were able to see this change much more quickly. And so it was occurring somewhere between 2 to 4 micromolars. And then it took a lot longer for the tert-butyl to actually work against just the strictly DNA. We assumed that when we would test this against the breast cancer cells, we would see the exact same thing. However, that was not the case. These represent 2 different epithelial breast cancer cell lines. And within these cell lines, we see that once again, our ligands are not the most effective, which is very good. And then when we get our copper complexes in, and we see that this particular line, which is the tert-butyl, and then this line, which is the tert-butyl, was much more effective in a much lower concentration than the ethyl that corresponded. The ethyl was still effective, just not quite as good as the tert-butyl. And that most likely has to do with the difference in the sidearm and being able to permeate the cell membrane once it actually gets into the cells and not just working against cleaving the DNA. So I would like to thank Tennessee Tech Eureka for providing us money in order to do this research program, as well as Dr. Susan Papish at the University of Alabama, Birmingham for the crystal structure, and then Dr. Jeffrey Rice at Tennessee Tech for running our breast cancer cell studies. Do you have any questions?